Okay, to the example, case of example 5.10, which comprise a parallel plate capacitor. And because the dielectrics inserted between the two plates is made of a lossy material which has non-zero conductivity, we know that it not only produces the fundamental E field, it also produces the conducting current within the structure. So you have both the zeroth order electrical field and zeroth order magnetic field. By applying a time varying source, that is a voltage source with a sinusoidal variation such as cosine omega t, the zeroth order E and H field shall produce following higher order terms. They are referred to as the HY1 because the magnetic field is in the y direction, and DX1 which refers to the electrical field pointing in the x direction. So here are the first order terms due to the presence of zeroth order E and H field. However, we should know that because the dielectric has non-zero conductivity, the first order electrical field, EX1, will also produce a conducting current. And this current term shall produce the so-called complementary first order magnetic field. So it's referred to as HY1C, the complement term. So it's a supplement term for the first order magnetic field. So in this slide, you see we have the derivation of HY1C due to the presence of EX1. It's a conducting current. So down below is the overall first order magnetic field HY1, which comprises two terms. One is due to the time varying zeroth order electrical field, and the conducting currents due to the presence of first order electrical field. And by looking into the relations between magnetic field and the voltage source V sub 0, we can write up the relation between the current I and the voltage V across the parallel plate capacitor. And we can also identify the three terms here can be substituted with per unit length, equivalent capacitance and equivalent inductance, as well as equivalent conductance. So they can be identified as a combination of this. So here, this is the capacitance, this is the inductance, and this can be substituted with the resistance. So overall speaking, the relationship between the current and voltage, which can also be rewritten as the relationship of admittance Y of the structure, is in the form of J omega C plus 1 over R plus J omega L divided by C. So it can be equivalently represented by a circuit made of lump circuit element. That is using the R or C component to represent the impedance or admittance variation in this circuit. So using the relationship of the admittance, that is J omega C plus 1 over R plus J omega L over C, you can draw the equivalent circuit for this parallel plate capacitor. And due to the schematics also reveals that the presence of R and L over 3, the inductance and the resistance, are due to the conductivity of the dielectric. If the dielectric use is perfect, which has no zero conductivity, then the path on the Y can be eliminated because of zero resistance and zero inductance. You will have only the capacitance. Nevertheless, due to the presence of finite conductivity, you have the R in series with L over 3 term. And this result suggests that at a very low frequency, the circuit, the parallel plate capacitor, shall behave like a capacitor. Nevertheless, as the frequency increases, at a higher frequency, the inductive property of the circuit will also appear and dominate. So at a sufficiently large frequency, the circuit itself shall behave like an inductor instead of a capacitor. And if you include more terms, more higher order terms, then as the frequency still goes up, you will come back to the capacitive property. So the frequency dependence of a circuit is not, you can say the circuit property, the component property, is frequency dependent. It may switch or alternating between capacitive impedance and between capacity and inductive impedance. All right, so sometimes it's of interest to consider the equivalent circuit representation for the input behavior of a structure for frequencies beyond quasi-steady approximation. 还记得我们讲到 quasi-steady approximation 的时候，它的条件是什么？什么是 quasi-steady approximation 的条件？电路的尺寸，结构的尺寸。当结构的尺寸小于频率的1/6个波长的时候，或者说极小于对应频率的1/6波长的时候，我们说 quasi-steady approximation 是成立的。但假如你的频率够高，也就是波长够小，当你的电路结构的尺寸接近波长的时候，接近差不多1/6个波长以上，接近1个波长的时候，那么光考虑 zeroth order term 跟 first order term， 也就是光考虑 quasi-steady approximation 的 term 就不够了，你必须要考虑更多的 term 才能够有意义的、有效的来去估测这一个结构它的阻抗或者是说导纳的特性所以在这一个频段频率够高的时候呢，你就进入到所谓的 beyond quasi-static 超越这一个准进场的这一个范畴。所以我们接下来看的这一个例子它是我们前面所看过的电感性结构，也就是么字形的一个parallel plate 的 inductor 所以在这里头，我们只要去观察它的 higher order term， 在这里头呢，它那个结构物中间塞的是什么？没有特别指啦但是它只有 mu 跟 epsilon 所以它是一个理想的介电材质所以它没有漏电流所以状况会没有像 example 5.10 那么复杂所以它算是一个比较单纯的电感结构。但是在这里头呢，我们把 EX1 还有 EX3， 也就是把它的 first order 还有 third order term 都把它放进来了原因就是我们想要看，当频率够高，你的 EX3 third order term 不能够被忽略的状况底下，它的电路特性会长什么样子。你只要只是从 DC 或者准进场的角度去看它的话，它就是一个单纯的电感嘛，对不对 但这一个例子里头告诉你跟你讲的是，当频率够高的时候，它就不再只是单纯的电感。Alright? So here we have the representation of the first order and third order term of the electrical field. So the electrical field can be approximated as the summation of first and third order term, that is J omega mu L times I over W plus J times omega to the square times mu to the square, omega to the third, to the cube, times mu to the square times epsilon L to square, blah, 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 okay. A lot of terms, as you get a higher frequency. And you can, because since you can write up the expression for the total approximated electrical field, you can find out the voltage, the total voltage of the structure. Now that the voltage is what? Is not the same at a different location. As you can see in this integration, it's the voltage developed at a specific position. Where is the position? It's Z equal to minus L. So it's the left end of this inductor. So this is the voltage developed at the left end of the structure. If you are looking at the voltage in the middle or somewhere within the structure, the integrated result should be different, because as you can see in the previous slide, the electrical field is not homogeneous. It's a function of position Z. So the total voltage developed at a different position are not the same. And here we look at the voltage at the left end. So you substitute Z with minus L into the expression to get its first term and the second term. And we also substitute the representation of the structure's capacitance and inductance. So here's the expression for the inductance, and here's the expression for the capacitance. So you can substitute them with L and C in this equation. So here you have 5.117 J omega L I sub 0, and the middle parenthesis is 1 plus 1 over 3 times omega to the square times LC. So what is the implication of this result? It tells you that at a very low frequency, that is omega is small, or even at a DC, if the test frequency is DC, the structure behaves like an inductor, right? Because if omega approaches to 0, you don't have this term, you only have 1 over here. However, as the frequency goes up, omega becomes larger and larger. Then the importance of the second terms becomes higher and higher, and eventually the importance of the second term shall succeed the importance of the first one. So you will see that the structure may behaves like a capacitor instead of an inductor. So here is the relation. Again, we use the relationship of 1 plus x to the minus 1. If x is very small, approaches to 0, then it can be substituted with 1 minus x. So suppose the frequency is non-zero and it's not really large. No, it's not really large. It's not that large. Then the equation, the expression in the 5.117 equation in the previous slide can be written in this one as an approximated value. And you can see the admittance can be expressed as a parallel combination of an inductor and a capacitor of a value C/3. So the effective equivalent circuit can be drawn like this. So it tells you that even though the dielectric between the structure is perfect, is non-conducting, the structure still exhibits capacitive impedance as the frequency goes beyond the limit of quasi-static approximation. So at a low frequency, that is below the quasi-static approximation, the structure is a pure inductor. However, as the frequency goes up, it will eventually shows capacitive property due to the presence of higher order terms. All right? So that's one thing you should keep in mind. All right, so let's move on to section 5.6. We will introduce the idea of magnetic circuit. And here, this figure compares the conventional electrical circuit with magnetic circuit. I suppose you guys are quite familiar with electrical circuit because an electrical circuit is driven by a voltage source. And its signal or its energy exhibit or in terms of electrical current J, and within the circuit, the dominant term or the dominant field is electrical field, right? As a comparison, the magnetic field, the magnetic circuit is driven by what? Well, use your imagination and logic guesses. You can understand that for magnetic circuit, the driven force, the driven element is the electrical current. And the electrical current will produce what? Magnetic field. And the collection of magnetic field is referred as magnetic flux, 磁通量，磁场的集合形成这个磁通量，形成磁通量密度、磁通量 phi。Alright, so here is a review of the electrical circuit. So as I already mentioned, the electrical circuit is driven by electrical current source, and it produces electrical current, which also exhibits electrical field within the circuit. And one important thing is the electrical current only appears within the conductor. This is a property due to that the conductivity in conductors and non-conducting material, the difference is relatively large. As you can imagine, the conductivity within a conductor and non-conducting material is about 10 to the 18th. So it's a very large difference in terms of conductivity. As a result, the currents only confined within the conductor. In other words, if you use a scissor or any tool to cut off the wire, the electrical wire of an electrical circuit, then the cutting position becomes an open circuit, and the currents cannot get across the gap made with the scissor or any other tool. So the electrical current cannot continue within a non-conducting material。这句话对吗？啊，刚刚我们讲的是什么？对于电流、电路啦，就是对于电路啦 ，electrical field circuit 来讲，对于电路结构来讲，它的能量或者它的场是以电流的形式出现，而电流因为导体跟非导体的导电系数差了那么多，所以你只要把电线剪断，电流就过不去了。好，大部分的状况是这样子啦，对不对？啊，但是呢，电流一定要以电子流动的形式才能存在嘛？其实我们在上学期啊就讲过 displacement current 嘛，对不对？所以 displacement current 是以电场变化的形式，实电电场的形式存在的所以你可以想象，在那个比如说雷雨前夕当你要打雷之前要打雷之前，那个打雷之前会发生什么事？电荷的聚集嘛，对不对？那个电荷聚集其实就是 displacement current 的存在，然后当你的电场够强的时候，假如你是在大气的状况底下，当那个电场够强的时候，它其实是会形成什么？形成那个电弧嘛，所以电弧是什么？电弧就是电场大到可以把那个气体分子结构中的正离子跟负离子拉扯开来，变成 plasma， plasma 是导电的嘛，所以也不是说电流只能存在导体内部啦，在导体外部它也可以用 plasma 的形式，比如说我们刚刚讲的闪电啦，或者是你汽车里头的那个 spark plug 火星塞的那个gap 上面也是 plasma 所形成的电流所以当然啦，在一般的状况底下啦你还是需要一个导体来去形成电流的那之所以要讲这件事情，也就是说，在我们比较电路系统跟磁路系统的时候磁路系统它有一个比较好玩的特性，就是说它当然电路系统的话，它是电的两导体嘛，我们称之为 conductor。而磁路系统一般来讲会用所谓磁的两导体，也就是 magnet 磁铁，或者是说 ferromagnetic material 具有良好导磁性的材料来去做所谓的磁路magnetic circuit。不过 magnetic circuit ferromagnetic material 里头的介磁系数它的 permeability 跟空气的介磁系数只差了10的3次方、4次方、5次方之类的，有差别，差很大，但是没有像电路系统那么大。所以对于一个磁路系统来讲，就算它断掉了只要不要断的距离很大很大，那其实还能用。磁路系统那个磁场还接得上所以这是跟电路系统比较大的一个区别所以我们等一下来看这一件事情。Alright, so here's the drawing for the magnetic circuit. It has a circular magnetic core, and due to the presence of this helical structure with a conducting current, the current source provides, as you know, the direct product of a flowing current is what? Is the magnetic field. So this helical-like electrical currents around the magnetic core. This thing is made of the so-called ferromagnetic material. 导磁的材料 ferromagnetic material shall produce magnetic field as well as magnetic flux within this ferromagnetic core. And so you have magnetic flux going around in this magnetic core, and they are made of magnetic field intensity H and the magnetic flux density B and the magnetic flux phi, 磁通量 phi, okay? And one thing to be noticed that is the magnetic field is not strictly confined within the ferromagnetic material. It can go into free space. Nevertheless, even though that this is because the permeability, 介质系数 permeability between ferromagnetic material and non-magnetic material is only about 1,000 times. It's not that the difference is not that big comparing to electrical conductors. However, the difference is still large. So you can expect, even though the magnetic field shall leaks to the space, the amount of leaked magnetic field or magnetic flux is relatively small. Here is an example. In this place, you have two medium. One is free space, air, down below. The material down below is air. The material above is what is a magnet. Is a magnetic material. So it has a permeability mu1, which is much greater than mu sub 0. And the two arrow represents the magnetic flux density across the interface. And from Maxwell equation, which one? Let me think about that. Which Maxwell equation? Which? Oh, okay. The two. Yeah, we know that the divergence of B, divergence of magnetic flux density equals to 0, which means B1 N shall equal to B2 N. And if there is no current, at the interface, then we can have the relationship of H1T equals to H2T. The tangential component of magnetic field intensity shall be the same. So using the two boundary condition, you have the two equations. If there is no surface current appears on the interface, then the tangential magnetic field intensity H is continuous. So you have H1 cosine alpha equals to H2 cosine alpha 2. And the normal component of magnetic flux density B shall continuous as well. So you have B1 sine alpha 1. Sine alpha 1 helps to extract the normal component of B1. So B1 times sine alpha 1 equals to B2 times sine alpha 2. And if you look at the two equations together, dividing each other on the two sides, you have B1 H1 times tangent alpha 1 equals to B2 over BH2 times tangent alpha 2. And suppose that the two material has oh no, you don't have to assume that. And because the relationship between B and H is permeability mu. So tangent alpha 1 over tangent alpha 2 equals to mu2 over mu1. And because mu2 is air, which equals to mu sub 0, A new one is the permeability within a magnetic material which is much, much greater than mu sub-zero, which is about 1,000 times larger. Then this thing is around 0.001 or something smaller, some number smaller. So it's much, much smaller than 1. So we can conclude, due to this relationship, that alpha 1 is much smaller than alpha 2, which leads to the result that B2 is much, much smaller than B1, which means even though you can have some magnetic flux density outside of the magnetic material, the ratio between the leaked magnetic field intensity over the magnetic field intensity within the ferromagnetic material is approaches to 0. It's very, very small, right? And one thing that you need to keep in mind about magnetic material is, for magnetic material and non-magnetic material, the difference in its permeability mu is usually in the order of 1,000 or larger. 磁性材料跟非磁性材料，它的介质系数的差异大概是在1000以上。那就像你在讲导体跟非导体、电导体跟非电导体的介电，不是介电导电系数的差距是在10的18次方以上。但epsilon， 也就是介电系数的话，一般材料的介电系数大概都落在1到10之间。除了一些特别的人造材料以外，好，不过相较于电的导体跟非导电体，它的导电系数的差距有10的18次方那么大。磁场介质系数虽然落差大，但没有那么可怕。所以意思是什么？你的磁通量虽然大部分是在磁性材料里头，但是还是会有部分跑出来。所以在这一个状况底下呢，它就衍生了蛮多的应用电磁铁变压器啦、马达等等最大的特征是什么？这些有磁性材料的那个元件拿起来都重快快就重为什么？因为它用了ferromagnetic material 它基本上叫做3氧化2铁一些主要成分是氧化铁啦，当然有些磁性材料它会加了一些，像你那个冰箱磁铁那个磁性是不是弱弱的但是你现在到文具店有时候你可以买到那种强力磁铁嘛，对不对我以前在10年前有一次跟一个机械系的老师在聊一些研究合作的东西，然后刚好他是做材料的，所以他在他的那个黑板上面就有2块磁铁然后一个先去针把那个磁铁撒过来，弄剩2块大概10元硬币大小的2片薄的磁铁然后边在聊的时候，我就试着想要把那2块磁铁分开结果发现分不开2只手用力掰又掰开，然后那个机械系的周老师就看着我笑说：“你试试啊，你试试啊！”就是真的是拉不开所以当它的那个介质系数够大的时候那产生的磁场其实是可以很大的当然，你现在看到磁场最强是用什么做的？什么东西你会看到最强的磁场会在哪里？最强的磁场大概是那个医院的那个核磁共振 ，CT scan 所以当然了，你可能各位应该没有机会用到 CT scan 当然希望你在50-60岁之前也不要用到OK。但有的时候就比如说你骨折啊干嘛的，有的时候没办法还是得用那个时候你只要去做 CT scan 的时候，那个医检师就会很那个紧张的问你说你身上有没有什么金属元件比如说有没有打个什么金属钢钉之类的为什么？因为那个东西 假如有一点点的磁性的话，那进到那个核磁共振的机器里头，它就会产生很强的吸力哈。我记得我那一次好像不知道什么，反正我身上有一个很小很小的一个金属件啊，然后靠近那个机器的那个洞口的时候哈，就感觉到了那个力量啊哈，那个力量是什么？牺牲一下，差不多像这样。哦，那个力量其实是很大的哦。那个量，我印象中那个核磁共振的那个磁场哦，它是用超导做出来的磁场，大概是2 T 啦，2个特斯拉。哦，我们一般地球的那个背景磁场大概是在1/1000个特斯拉这个等级。哦，所以其实现在那个什么，现在那个关税贸易战不是美国要打中国，然后中国他们现在主要的反制武器就是那个吸铁嘛，对不对？那为什么吸铁重要？因为吸铁是用来做磁铁的，马达要做磁铁，所以假如你不出吸铁的生产不出口的话，那其实一些做马达的一些厂家就做不下去了，所以像这一阵子的话，是中国说好给美国，但是他给那些吸铁给美国之后，欧洲就没有，所以欧洲有一些汽车工厂就可能停摆了哈，那个生产就受到中断。为什么？因为马达做不出来。OK， so but the ferromagnetic material is quite important. Considering the production of modern day industry. So let's look at the, again, let's review the electrical circuit again. So here we have the equation for what? For the computation of electrical potential. The line integral of electrical field shall produce the electrical potential. So for this electrical circuit, the voltage developed across the gap can be found as the EM, which is a consistent electrical field intensity reside within this core, within the circuit core, times the length of the circuit, L. So the current, the conducting current, JC, C refers to conducting current, shall equals to sigma times EM, is proportional to the conductivity of the conductor and the electrical field intensity within this core, EM. So using this expression, you can find out the relation between the current I and the voltage V equals to what? Equals to sigma times A over L. And we know that the ratio of voltage over current is what? Is the resistance. So for this circuit, the resistance can be expressed using the geometry parameter such as L, and A is what? A is the cross-section area of the core, of the conductor core, and the conductivity of the material. However, this expression, even though that you are familiar with, is only good for DC condition. Because if the current is alternating one, if this is the AC current, then the current distribution will be concentrated near the surface of the conductor. And for DC case, the current can be evenly distributed across the conductor. So here we have A. It's proportional to the area of the cross-section area, but for alternating current, it's not related to the cross-section area. All right. But anyway, for the DC current, you have this result. This is the representation of the resistance. So let's look at the magnetic current. As we know, magnetic circuit is driven by magnetic flux source, which is current source times the number of turns. Why? Because the magnetic flux produced from one single turn is not that large, and it's not safe to apply a large current. Therefore, in order to strengthen or to increase the amount of magnetic flux, instead of increasing the electrical current I directly, we use helical structure, that is, having more turns so that we can produce a larger magnetic flux within the structure. Alright? 好，所以为什么？因为你要注意那个被电死其实不是因为电压，是因为电流。你可以想象到电压是比例于电场强度，但就像我们开学的时候讲的，电压是假的电压是假的电压不是真实的东西。但高压电只要电流够大的话，一样会死人。OK， 但即便电压不大，电流够大的时候你的能量是什么 ？I 平方 R 嘛所以只要你身体有相当大的电阻然后又有够大的电流通过，那就会在你身上消耗掉足够多的电能，这些电能会转换成热能来去伤害你的皮肤或者是神经系统对人体造成伤害所以在我们那个我想听有人讲说台科的电机系跟电子系差在哪里？你们知不知道？有一个讲法就是电机系毒不死人因为我们没有光电因为刚好我们整个电机系没有人在做光电电子系呢，他们是电不死人，因为整个电子系没有人在做 power， 没有人像我们家族是做大电的嘛所以这两个是台科的电子跟电机的主要区别啦其他所有领域几乎都有 overlap 都有人在做了Alright, so let's look at this equation. So we begin with the Ampere's Kirchhoff law. The line integral of magnetic field is should be the same as n times I sub 0, which you can recognize Ni is similar to V, similar to voltage. And the things goes within the magnetic circuit is magnetic field, alright? So the magnetic field intensity can be found by Ni sub 0 divided by the length of the circuit, of the magnetic circuit L. And the corresponding magnetic flux density B can be found by the product of permeability mu with magnetic field intensity H. So we have the following expression. And the total magnetic flux phi can be found by the product of magnetic flux density and the cross-section area of the ferromagnetic core, the area A. So you have this relationship by identifying that Ni over phi, the source over the flux, the ratio of the source and the flux. You can identify this new parameter, which is R in calligraphy type 花体字calligraphy type 花体字的 R， 那这个 R 的话在课本上是叫做 reluctance， 那中文的话你可以叫它是磁阻所以 reluctance 在这里指的是磁阻也就是电流有 源磁流源不是电流源了，磁流源 over 磁流大小的比例So the reluctance derived within this magnetic circuit is L divided by mu and A, and you can find it's similar to the expression of resistance in electrical circuit, which is the ratio of L over sigma times A. So therefore, you can compare resistance within electrical circuit with reluctance within magnetic circuit. And the conductance, conductivity, can be compared with what? Permeability in magnetic circuit. And you can draw the magnetic circuit of this one like this. So you have, that's probably the simplest magnetic circuit. You have magnetic flux source Ni sub 0 time, and here is the reluctance R, and the things goes around in the magnetic circuit is magnetic flux phi. All right. So then we can compare the electrical circuit and the magnetic circuit with all the different parameters. So in the electrical circuit, the current source, electrical current source, is driven by voltage V sub 0, and in the magnetic circuit, the magnetic flux is driven by Ni sub 0. And within the electrical circuit, the dominant field is electrical field, and it's compared with H. And here you have a conducting current, and here you have a current density Jc, and compared with magnetic flux density B. And the material parameter are conductivity sigma and permeability mu. And the things that goes in the circuit are electrical current and magnetic flux. And the so-called resistance is compared with reluctance. All right. Next, let's take a look at example 5.11, which is an example problem for the magnetic circuit. This thing is, well, you will definitely see this kind of circuit in your midterm. Alright? 所以至少20分呢。你看考古题有吗？我过去的10年，每一年都有这一个东西当然不一样了，每年不太一样所以该打起精神来了OK。So let's take a look at example 5.11. So here you have a magnetic core made of 3 legs. The 3 legs has different cross-section area size. The middle one is larger, the other 2 on the sides are smaller. So as you can see, the geometric parameters specified in the example, the problem are A2, the middle one, has a 6 centimeter square cross-section area. And the other 2 legs has the cross-section area 3 centimeter square. The lengths L1 and L3 are 20 centimeter, beginning from here to here, right? And the length of the middle one is 10 centimeter. Note that on the right-hand side, the leg 3, the 3rd leg, has a gap, a tiny small air gap in the middle, which has a length of 0.2 millimeter, a relatively small one. However, you can imagine that the presence of this gap shall establish is relatively important to the analysis of the circuit. And the problem asks you to determine Ni value, that is, the driven force of the magnetic flux, Ni in the middle. Well, you don't have to specify N, or if you specify the number of N, you we shall know the magnitude of the current I because of the requirement. So we need to know, or we want to know, the value of Ni to establish a magnetic flux of 4 times 10 to the minus 4 rep in the gap area. 所以这一题的话，就是说，在这一个几何状况底下，假如要在那个右边的那个缺角的地方建立起一个4乘以10的负4次方的韦伯的这个大小的磁通量 phi 磁通量 phi 的话，那中间的那一根它绕过去的那一个磁流源 Ni 的值应该是多少 ？OK， 好了，我们先休息一下。